This will be our fourth lecture, and the way I would like to begin is by quickly reviewing the material that we have covered in the first three lectures, and then we will continue what we were doing in the last lecture. So, if we can go down to the screen here. So, here is a summary of what we have done up to now. So, we covered in the first lecture, which I entitled Hamming Weight and Hamming Distance, we looked at the flow chart for the course, we looked at the binary symmetric channel, then we looked at modulo to arithmetic, how to work with vectors whose symbols are binary. We defined what it means to talk about a binary block code and also the parameters of a block code. Then in the second lecture, we looked at some example codes and their parameters, the repetition, single parity check and the Hamming codes. We looked at the minimum Hamming distance of a code, which is defined to be d min, and then we looked at the relationship between the minimum distance of a code and its error correction capability. Then in the last lecture, this should be 3. In the last lecture, we talked about mathematical preliminaries, groups. So, we began by completing the earlier proof on the relationship between the minimum distance of a code and its error correction capability, and then after that we started talking about groups. Now, these are algebraic structures, and so you will have to be a little bit patient because it is good to have the algebra behind that is behind all the theory that we will study. So, we will go through that algebra, it will take us 2 or 3 lectures, and then we will come back to the codes, and that will allow us to progress so much faster. So, getting back to the pad, so we started talking about groups, and we first discussed axioms that go into making up a group. We looked at examples and then some derived properties, and so today we will continue from there. So, with that I am going to close this particular file, and we will go on to our lecture pad here. So, this is our lecture pad. Let me so quickly reviewing this, these on this side here you see the axioms that define a group, and then we looked at some examples. We looked at derived properties, that is properties that follow from the axioms, and that is about where we are. So, we will continue from there. So, this then I will title this lecture as subgroups and equivalence relations. But first, continuing on from where we had left off last time, I would like to discuss one further example. So, a further example of a group. This is the case when we are looking at the group and the operation is Z sub n, and I will put a star on top and this. So, first of all, with regard to the notation, this thing here is the non-zero, the set of non-zero elements in the set of integers modulo n. So, you can treat this as precisely the set 1, 2, 3 all the way up to n minus 1. So, you exclude. So, in other words, this is z sub n, but with the 0 element removed. And here this thing here, this operation is multiplication. So, earlier we had looked at addition, but this time we are going to look at multiplication as our operation. So, of course, one question is, well, what is n, right? So, n is an integer. So, we will look at an example within an example. So, let us say we look at the case when n is equal to 6. So, we are looking at z6 star under multiplication, and the question is, does this form a group? Now, recall that in order for something to be a group, it had to satisfy the following axioms. 1, it had to satisfy the axiom of closure. 2, the multiplication, the operation had to be associative. Then you needed the presence of an identity element. You needed the presence of an inverse, and in the case of an abelian group, you needed that it be commutative. Okay. So, basically there are 4 operations that you need to check. And so, right away when you look at, so of course, Z6 star is this set, it is 1, 2, 3, 4 and 5. So, 0 is excluded. Right away you see that if you multiply 2 by 3, this is 0 modulo 6, and that is a problem, because now you are multiplying 2 elements in this set, but what you are getting is an element outside the set. So, the closure requirement is violated. So, this violates closure. So, the conclusion is that this is not a group, therefore, not a group. Now, if you look at this proof and say, well, why is it that this proof failed? Well, the proof failed because we started off with n equal to 6. Now, 6 is the product of 2 integers. So, that seems to suggest that, well, maybe if I chose an integer n which is just not divisible, then perhaps there is some hope that this violation would not occur. All right. So, we will look at a slightly refined example. So, now we look at Z p star under multiplication, where this time p is a prime. Now, it is typical in algebra to reserve p or q to represent a prime. So, in this case the integer n is replaced by a prime p. And again we have to check for the following axioms. You have to check for closure, associative property, the presence of the identity element, the inverse, and whether it is commutative if you want it to be an abelian group. and this time you can check that as far as closure is concerned. So, if you take since I do not want this to be a formal proof, I just want to convey the idea to you. So, let us take an example when p is 5. So, it is an example within an example. So, it is Z5 star with a dot, and now the question is multiplication, is it closed? So, is it possible that A into B is 0 mod P without either A or B being 0 mod P? But this is clearly impossible, because when you say A into B, what you really mean is the remainder when you multiply A times B and divide by P. Okay. This is how you define it. Let me put down multiplication here. So, this is ordinary multiplication, and that is what you really mean when you write down A times B. So, if the product is 0 mod P, that means that there is no remainder, which means that P divides A times B. Okay. So, so A times B equal to 0 implies that P divides A B, but you know that P can divide a product of two integers if and only if P divides either one or the other of them, or both. But that means that implies A equal to 0 mod P, or else B is equal to 0 mod P. Okay. So, therefore, what we found is that A times B equal to 0 cannot happen, because A and B are in Z P star. Okay. So, the conclusion here is that closure this time is satisfied, there is no problem there. You can similarly check that the associative property is satisfied, and also the identity element is just 1. So, that leaves us with the question of inverse. Okay. And how about the inverse? So, let us look at the inverses. So, again let us look at the case when P is equal to 5, and supposing we want to know what is the inverse of 2. So, what we can do is, we know that Z P star consists of 1, 2, 3, 4. So, we take 2 and multiply all these elements into it. So, 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6, which is 1 mod 5, and 2 into 4 is 8, which is 3 mod 5. Now, as you look at this, you will notice that all the results on the right hand side here are different, and in fact they have to be, because so note all entries on the right hand side above are forced to be distinct. Since by cancellation two into A is equal to 2 into B implies that A is equal to B, because otherwise else this would imply that 2 into A minus B equal to 0, which is impossible. Right. So, again let me repeat. So, we are now looking at ZP star when P is a prime, in particular when P is equal to 5, and we want to check whether the axioms of a group hold. So, we have already checked closure, the associative property, and the presence of the identity element. So, the identity element is equal to 1. So, there is nothing much there. How about the inverse? So, that is the question we are trying to investigate, and I am going to illustrate the general proof by looking at the example when P is equal to 5. Supposing you are trying to look at 2 inverse. Now, to find 2 inverse, what you can do is you can multiply 2 by all the non-zero elements in here in succession, and it has to be that all the elements on the right hand side will be distinct, which means that all these elements must appear on the right hand side exactly once. But in particular, what that actually means is that even 1 will occur exactly once. So, that means that there is some element such that 2 into 3 is 1. Now, that means that 3 is actually 2 inverse. This group by the way is commutative. This group is commutative. So, for the inverse I only need to check that I get 1 when I multiply on the right hand side. So, what this actually implies, this implies that 3 is 2 inverse. Okay. And in general this proof can be extended to show that inverses exist in general. Okay. So, a similar proof can be used to show that every element of ZP star has an inverse, and hence ZP star is a group under multiplication. Okay. So, that concludes yet another example of a group, and so now what I would like to do is continue by talking about subgroups. So, we will begin with the definition. A subgroup H dot of a group G dot is a subset H of G such that, and I will often abbreviate such that by writing S dot T dot, such that H is a group by itself. Okay. So, that is the definition of a subgroup, and let us look at some examples. The first two examples are trivial examples. The H is equal to just the group itself. That is clear, it is clearly a subgroup. The second example is the case when H is a set that consists of only the identity element of G. So, here E is the identity element in G, okay. And you can verify that this forms a group. So, I will just say that it is easy to check that is a subgroup. Okay. So, these two examples, the two extreme cases when the subset H of G is all of the group and the subset H of G consists of just a single element, these are the two extreme, and these are called trivial examples. Now, we will look at a couple of other examples, but before that let us get into another issue, which is how do you test for a subgroup. Now, there is the brute force way, the brute force method would check the following. It will check to make sure that closure, the associative property, the identity element and the inverse all exist. But there is a cleverer method of doing it. There is a better method, and that is to make use of a lemma. So, I will actually put this down as a lemma. Let me, before I do that, perhaps I should make one clarification. Instead of saying H plus is a subgroup of G plus, we will simply say that H is a subgroup of G. Okay. So, I mean it is just as a short form. Okay. Strictly speaking, when you talk about a subgroup, what you really mean is that there is a group, there is a set and there is an operation, and then when you are talking about a subgroup, you are looking at a subset of that main set, universal set, and then you are looking at the same operation and you are trying to show that that is a group. So, strictly speaking, one should talk about, going down to the pad, we should talk about H dot as a subgroup of G dot, but that is too cumbersome. So, we will just simply say that H is a subgroup of G, all right. So, here is a lemma. So, the brute force way is to actually look into H, and maybe I should also draw a small picture here. So, here is a picture, that is, you have your group G, and then sitting inside this you have a subset H, and what you want to do is test whether the elements in this subset actually form a group under the same operation. So, the brute force way is to apply all the 4 tests, but a better way, a much simpler method, is to apply the following lemma. Which says that H subset of G is a subgroup if and only if A, B in H implies that A times B inverse belongs to H. So, it is a simple test. In some sense, you have reduced the requirement of checking 4 things to just checking a single item, okay. And you will see that it is quite useful when we come down to checking whether something is a linear code or not. So, that is an application here. So, let us go ahead and prove this. So, the proof. Now, again let us keep in mind that we need to show that the single test is a substitute, is a valid substitute for the axioms, okay. Which are the axiom of closure, associativity, the identity element, and the inverse, okay. Now, as far as closure is, so let us we will not necessarily tackle them in that order. It is convenient to actually tackle the identity element first, okay. So, when we set setting A equal to B implies that setting A equal to B implies that A B inverse is equal to the identity, which implies that the identity element belongs to H, okay. So, thus we have checked that the identity element belongs. Next, setting setting A equal to the identity, because now that we know that it is there, tells us that B inverse belongs to H. So, that gives us that the inverse is also there. Now, the associative property is something that we do not have to test for. The reason being that if you think about it, I mean there is a property of associativity with respect to multiplication. Remember that the associative property requires that the way in which you group elements together before multiplying does not matter. So, since that holds for the parent group, it also holds for the subset. So, we do not really have to test for that, right. So, I am just going to, without any further argument, we will just put down a tick for that. So, now we come down to the question of closure. So, closure means that given that A and B are in H, you have to show that A times B is in H. So, what we will actually do is, so for closure, given A B in H, we know that B inverse belongs to H, which implies that A times B inverse inverse belongs to H, which of course implies that A times B belongs to H, and we are done. Okay. So, that is how you take care of closure, because the inverse of the inverse is the element itself, as you can check. Okay. So, that finishes that proof. Now, okay, so in summary, if you want to check that something is a subgroup, you will just apply this one test from now on. There is a further simplification in the case of groups that have a finite number of elements. And we will put down a lemma for that. If H is a finite subset of G, then H is a subgroup of G if and only if A B in H implies that A times B is in H, or in other words, in the particular case of finite subsets, it is sufficient to just check closure. Now, in the interest of moving along, I will not prove this. I will leave you to prove this as an exercise. And perhaps as a hint, I will just ask you to consider, given A in H, consider A squared, A cubed, and so on. This is an infinite sequence. It is an infinite sequence, yet H is finite. Use this. Okay. So, you might enjoy trying that out on your own. So, basically you look at the sequence A squared, A cubed, and so on, which goes on to infinity, but all the elements belong to H, because we know that H has the property that if A B belongs to H, then A times B belongs. So, in particular, if A is equal to B, then A squared belongs, A cubed belongs, A to the 4 belongs, and so on. And this is an infinite sequence, and but on the other hand, since H is finite, it must really be finite. Okay. So, use that property. In other words, there must be some repetition in this sequence and you should be able to use that. Okay. Now, we are going to move on to the topic of cosets. We will begin with the notion of an equivalence relation. A relation R on a set A is a subset of A cross A. Okay. This is also called the Cartesian product of A. Of A with itself. So, the Cartesian product simply means that you just take all pairs A B where A comes from A and B comes from A. i.e., R is a subset of A cross A. If AB is in R, which means that A and B are related by relation R, we will write A equivalent to B. Okay. And let me at the same time introduce some other notation. The notation is that EB is the set of A in A such that AB belongs to R. So, in other words, E sub B is the set of all elements A which are related to B through relation R. Okay. So, loosely speaking, EB is the set of all elements in A that are related to B via the relation R. Okay. All right. Now, I claim the following. If R is an equivalence relation, okay. Let me just backtrack. I think I went ahead of myself here. Before I can make this claim, I was going to make a claim about a property of these sets E sub b, but I need to introduce another notion first. So, let me just erase this, we will backtrack, we will come back to this point. Okay. There is one other point that I need to take care of. So, within the class of relations, there is a class of relation that is called known as an equivalence relation, which satisfies certain additional properties. A relation R is said to be an equivalence relation on A, provided that all the following conditions are satisfied, namely 1, that A is equivalent to A. This is called the reflexive property. 2, A is equivalent to B implies that B is equivalent to A. This is called the symmetry property. The third property is that if A is equivalent to B and B is equivalent to C, this implies that A is equivalent to C, and this is called known as the transitive property. Right. All right. And we will look at some examples very soon. So, now we are ready to make the claim that I had stated earlier. Claim if R is an equivalence relation, then if AB belong to A, then either EA is equal to EB or else EA intersect EB is the empty set. This is like an all or nothing property. Okay, so, let me just try to make the picture clear. We first defined a relation on a set R. We said a relation means a subset of A cross R. So, it is just pairs. We just pick certain pairs and say that they are related by relation R. However, when the relation has certain properties, namely that if A is related to B, then B is related to A. A must be related to itself. If A and B are related, B and C are related, then A and C are related. If the relationship is of this type, and this is the type that we will be interested in coding theory, then it is said to be an equivalence relation. All right. So, this is said to be an equivalence relation. So, if R is an equivalence relation and if A and B belong to A, then either EA equals EB or else EA intersect EB is the empty set. So, that means that there are only two possible pictures that you can have in mind. So, one of them says that the picture is like this: you have EA and you have EB, and they are one and the same. Or the other property is, so the other property is that you either have EA like this and EB like this. So, either they share all elements in common or nothing, and it is really quite easy to see why this must be the case. So, we will just sketch the proof using the figure. And the figure is basically this. So, let us say that suppose the situation was like this. Supposing there was an element x that belonged to both EA and B. Okay. Now, this is the equivalence class of A. So, certainly by the reflexive property A belongs here, and we know that B belongs here. All right. So, what this figure seems to suggest is it possible that they can have some elements in common without being the same? Okay. So, these are elements in common. Now, certainly if they are not the same, there must be some element, some pair of elements which do not belong to the intersection. So, let us say, so the A and B may or may not belong to the intersection. So, I am not going to use them, but let us pick two other elements. We will pick two other elements. Let us say we will call this Y and Z. Okay. So, there are, since if EA is not identically equal to EB, this must be the case. All right. But we know actually I guess I do not really need the presence of two elements here, just one will do. Supposing there is an element Y which does not belong to their intersection. So, let me clarify that by writing that down. Suppose Y belongs to EA, but not to EB. Okay. And suppose X belongs to EA intersect EB, but then this implies that Y is equivalent to X, and you have X is equivalent to B, implies that Y is equivalent to B, implies that Y belongs to EB, which is a contradiction. Okay. So, let me just run through that again. So, let us say we are worried that the following picture exists. In fact, to make things clearer, let me remove this Z, which I just pointed out was not needed. So, let us get rid of the Z. Now, supposing there is an element Y which belongs to A, but not to EB. Okay. And we know, however, that there is something in the intersection, and we have called that X. So, x belongs to the intersection, but this figure tells you that y and x are related, but b and x are also related. So, y is equivalent to x is equivalent to b, and by the transitive property that means that y is equivalent to b, but that means that y belongs to EB, but that is a contradiction because we assume that it belongs to EA but not to EB. Okay. So, what does it contradict? It contradicts the possibility that when there is intersection between EA and EB, that there is an element y in EA which is not in EB. So, the only possibilities that exist are either if there is something in the intersection they are completely the same, or else to begin with they have nothing in common, that is such an element does not exist. Okay. All right. So, as I said, that is a sketch of the proof. You can actually fill in the details on your own. All right. Now, I want to talk about a type of equivalence relationship which is useful in coding theory. Okay. So, cosets of a subgroup. So, let G be a group and H be a subgroup. Of G. Let us define A equivalent to B if A times B inverse belongs to H. Right. Now, or in other words, i.e. R is the set of all pairs AB in G cross G such that A times B inverse belongs to H. Now, what I would like to convince you is that this is an equivalence relation. So, claim this is an equivalence relation, right? Proof. Now, we have to show the reflexive, the symmetry and the transitive properties hold. So, is A equivalent to A? But that is the same as saying that A times A inverse belongs to H. But that is true because but A times A inverse is equal to E, and E belongs to H since H is a subgroup. Therefore, A is equivalent to A. Okay. So, we have shown that the reflexive property is true. How about the others? The symmetry property, if excuse me, the symmetry property, if A is equivalent to B, does this imply B equivalent to A? So, that is the same as asking the question A B inverse in H, does this imply that B A inverse belongs to H? But this is true, but since A B inverse is B A inverse and H is a subgroup, this implies that B A inverse belongs to H. Therefore, yes, the symmetry property holds, right. So, we verified the reflexive, the symmetry and the transitive property. Okay, again, to establish symmetry we have to show A B inverse in H implies that B A inverse in H, but since this is just the inverse of this, if this belongs then the inverse also belongs. Okay, so, there is no problem there. So, that leaves us with the transitive property. So, the transitive property asks if A is equivalent to B, B is equivalent to C, does this imply that A is equivalent to C? Okay, but A is equivalent to B is equivalent to saying that A B inverse belongs to H. This is equivalent to saying that B C inverse belongs to H. Therefore, A B inverse times B C inverse belongs to H, since it is a subgroup, which implies that A times B inverse B C inverse belongs to H, but this is the identity, but this middle term is the identity. So, this implies that A C inverse belongs to H, but that means that A is equivalent to C. Okay. So, we have actually proved what we wanted to actually prove. So, all three properties are actually satisfied. So, we will put a tick mark on this one as well, and so we have established that this is an equivalence relation. All right. Okay, very good. So, I think that we are close to winding up our time. I think this is a good place to stop. So, perhaps I should just quickly recap. So, what we did today was we were continuing our discussion on mathematical preliminaries. We started out in the last class by talking about groups, and so today we talked about subgroups and relations. Before entering subgroups, we talked briefly about a further example of a group. So, in the next class what we will do is we will continue further this example of an equivalence relationship and introduce the notion of a coset of a subgroup. Okay. So, with that I will leave you. So, we will catch up with you again in the next class. Thank you.